So first is the problem. So if you're familiar with blockchains, you'll know that um, they aren't necessarily, so yeah, the basic problem with blockchains is that they aren't necessarily geared towards high throughput, high transactions. They have a lot of security, it's a novel security, novel permissionlessness, but they aren't necessarily designed for high throughput. So this is a kind of a comparison slide. So you can say Visa has, there's different measures, but they say, on average, they're doing 176 transactions a second worldwide, but they've tested it up to 24,000. So that's a lot of transactions. And the settlement time could be seconds, but the reason I put 90 days there is because with a credit card, it isn't really settled until if you buy something, it could be charged back. So that's one difference with blockchains. For instance, if you have a blockchain transaction and it settles, it's settled. There's no reversibility in the typical way people think about blockchains. PayPal I put on there too. I don't know, that's used so much here in Sweden. I didn't put Swish on there. couldn't find any numbers for Swish, but I imagine it's got similar characteristics. It's fast, it's irreversible. So this is traditional centralized technology, is very, has this throughput. And to propose something like a blockchain technology as a replacement for that, for purchases or what have you, then you need to be able to match that throughput. I also put on here international wires because that brings up another aspect of blockchains which you don't get necessarily with Visa. Well, I guess you can do international purchases with Visa, but if you wanted to wire money from your bank, it's going to take 1 to 2 days, and there's going to be a fee. So it says about 133 international wire transfers per second. So at any rate, you can sort of get the feeling of what a traditional payment system requires. And so for a blockchain to replace that, it's going to have to do better than 3 to 7 per second, for instance. I mean, we're an order of magnitude slower with a Bitcoin blockchain. Ethereum does a little bit better, 15 to 25. But there's debate about whether that is sustainable. I mean, there are some of these blockchains with really fast times in their blockchain protocol can suffer from other problems. So it's a pretty intrinsic problem overall to the blockchains. So what do we mean by a blockchain transaction? So at the top level there, I've got a transaction. So this is just one person paying another person. And when they basically sign a transaction paying from one to the other. It goes to a blockchain, goes to whatever blockchain, and then the blockchain has to come to a consensus that all the nodes, so it's replicated. That transaction is copied not just to a Visa single centralized database, it's copied to thousands of individual computers run by people who don't know each other or don't trust each other all over the world. And then they come to a consensus about the ordering of these transactions. And that's how it becomes settled. So when I said it's an hour on Bitcoin to settle, that means it takes an hour for all of these machines to come to a shared consensus about that transaction being final and settled. And they're gossiping on the what I put as zero, on layer 0. They're gossiping this around over the internet. So there's actually speed of light time that comes into play too. I mean, when you've got computers all over the world settling transactions, there's actually delay just in the communication and sending data back and forth. So there's some real world sort of low level limits, and then there's the consensus. The consensus is the slower of the two, but anybody who tells you they've got a blockchain that can settle in like half a second hasn't done the math of how long it takes to send that around the world, to every machine in the planet. So anyway, this is the source of your delay in settling any sort of transaction on a blockchain. So this is from a presentation. These numbers are from a presentation done by Joseph Poon and Thaddeus Drya. So these are the guys who were first to introduce this notion of a second layer system for settling transactions. And they did some math using the Bitcoin blockchain. I mean, I think the math is pretty similar on most implementations, though. So using a current implementations of Bitcoin, you could get, so you could get about 220 million transactions in the current block. So I didn't mention that before, but there isn't just the speed issue. There's also, you can only settle so many. The other limit is how many transactions you can record. So these are recorded in they call a block. So there's these blocks that are produced every 10 minutes. and there's a limited finite space for those, and that limit is there for security reasons. If you made the blocks infinitely large, so if you made it 1.6 gigabytes, then you could maybe get 1 billion transactions a day. But the problem is, and they said that would be enough for a metro area. That was how they kind of measured these things. But the problem is, if you had such large blocks, if you were settling so many transactions, not only would you have a time delay, but you would the only machines that could be part of this network would be mainframe computers. You couldn't necessarily expect everybody to have 87 terabytes hooked to their personal computer or hooked to their mining computer to record these transactions. It's different. A company like Visa that has a centralized database, they have the resources to record that, but it's not necessarily going to be true for a distributed, decentralized payment system. So the time is also a factor of storage. And this is, if you remember, there was something called the scaling debate in 2017 that where there was a lot of controversy in the Bitcoin world, at least, about how you should scale up these networks and whether you should scale them on this layer 1 where you basically make the blocks bigger or more often, or whether you do it some other way. So that's why I'm discussing here about the fact that you've got different sizes come into play. And the final sort of number they give there is if you had 7 billion people on the planet and they do 2 blockchain transactions a day, you would have 24 gigabyte blocks. So you can see that as you scale these blockchains to the whole world, if you really expect the whole world to basically do commerce with a blockchain, it just doesn't scale. You couldn't expect, even the other argument, I suppose, is that technology is getting better and better, but the growth would be too large. It would outrun what you could expect to have on, say, your cell phone or on your personal computer. So these guys, Joseph Poon and Thaddeus Draya, they proposed another layer to solve this problem. So you're still doing your transactions between 2 people at a time, but now you create a network of these pairs of people doing these transactions, and you let them settle the transactions without settling it on that first layer. So you're basically, if you're familiar with, like in computer science, there's this concept of caching. So you're doing a lot of transactions, and then you're caching those transactions. You're not actually writing them out to your blockchain, and you're essentially netting out your transactions between multiple people, and then periodically, not once a day, maybe once a year even, you're settling those transactions. So that's the way that is being proposed when people talk about layer 2. They're talking about this layer of this network that runs separate from the Bitcoin blockchain. But it isn't, an important note is that it isn't a different blockchain. It's actually a cache of valid blockchain transactions. So people are making transactions like they would on the first layer. They're just not writing them out. They're just not settling them. So at any time, anybody can take these transactions and write them out. But it's a way to avoid doing that because it's expensive and because it's slow. So that's what I'm going to try to get into here is, what does it take to build this network that is an off-chain settlement for these transactions? So the way it's generally conceived, so there's different technologies. There's Lightning is what they call it on Bitcoin blockchain. There's something called Raiden on the Ethereum blockchain. I think Litecoin, which is another blockchain, also uses Lightning. So these technologies are fairly general to the concept of the concept of these can be applied to different underlying blockchain technologies. So one key concept is a payment channel. So this is just between 2 users can establish a payment channel. And the key feature that your blockchain would have to do a payment channel, there's a few, but the key one is what they call a multi-signature address or multi-signature account. So this is it's been a long time since you've had checks here, but in the US we still use checks. And there's this idea of 2 signature checks. So it's the president and the treasurer, and if they both co-sign it, then it's a valid check. So the same concept exists in a cryptocurrency or in a blockchain. So 2 people can basically put their funds into an account or put them into an address, and only if they both sign can it be spent. And so that's So that's the fundamental way you make these payment channels. And so the first transaction that they say is on-chain prepayment. So the first thing they do is the two people who want to establish a payment channel will pre-fund some channel between them. So they'll usually one is going to pay another. So instead of if I owe you, if I'm paying for something that's very inexpensive, I want to pay you a kroner, I'll give you 100 kroner, but I'll prepay you 100 kroner, and that's sort of that's my tab at the bar, as you will, with that person. So you've prepaid, and that's called a setup transaction, and that is on first layer. So that's one transaction that has to go on the first layer. But then after that, subsequent transactions are these update transactions. Those you're not actually writing anything to the blockchain. You're just updating the state of that payment channel with the other person. And then at some point you're going to close out your tab. Then you do a settlement transaction. So you can basically do a setup, close, and an unlimited amount of these update transactions. So it's that unlimited update is where you get the leverage to do more transactions per second than you would, because it's only the sort of opening and closing that actually has this delay on the blockchain, or takes up space on the blockchain. And then I also have written down here uncooperative close. And one of the key difficulties with setting up this system is, what do you do if this person who you've signed to create a payment channel with disappears, or they're malicious, or how do you basically secure it? Doing this in a secure way was the challenge that people tried to solve. So this is just a representation. So you can see that in this example, Alice and Bob, your standard cryptographers, in this case, Alice is funding a shared account. So each of these circles you can think of as an address or an account that one or the other controls. And the one in the middle, they both control. And key to doing this initial setup is what happens if Alice puts in 10 to the shared account and then Bob disappears. Because it takes 2 signatures to spend, Alice would be stuck. Or maybe Bob can come back and say, give me half, because otherwise I'll just walk away. So the way these payment channels are set up, part of the setup is that they pre-sign this bottom set of transactions. So before Alice transfers money into the account, she has Bob pre-sign a transaction that spends and refunds the money back after some delay. So now the money can be safely deposited in there, and if Bob disappears, Alice only has to wait some amount of time that she's agreed to, and the money will come back. So this is part of the security mechanism that goes in there, and there are more uses of those time delays, but that's the most important one, is that there's a refund for the first person. Just as an aside, one of the reasons this wasn't, so this talk that Tad Dryda gave in 2015, that was 2 years ago. Why didn't they have payment channels sooner, or why didn't they have these Lightning Network, these payment channel networks sooner? And one of the reasons is because that second transaction, that refund transaction, depends on this shared transaction. And the way in Bitcoin, there was a bug basically, or there was a thing you couldn't do in Bitcoin, which was you couldn't write a transaction that depended on a previous transaction. If you've heard of this term malleability, people could malleate a transaction in such a way that you couldn't rely on it. You couldn't chain transactions ahead of time. So that's a feature that basically was fought over quite a lot last year in the Bitcoin world, and they finally got the fix that allowed that to happen. And that's why now this year you're seeing a big push for something like Lightning and these second layer protocols. So like I said before, once you've locked that in, now Alice and Bob can negotiate. They can say, Alice can say, I'll give you I'll give you one credit if you give me a minute of cell phone coverage, or whatever it is you're negotiating over. And so then Alice would basically sign a transaction saying, okay, now the split, if we walk away, the split is going to be 9-1 instead of 10-0. And then, of course, Bob, who gets the transaction, they want 1, so they sign it, and they don't have to put it on the blockchain. So this is where the scaling comes in. So they just hold it. They just put it in their back pocket, and they wait. And if Alice wants to spend more, they can spend more. I didn't actually show it on this slide, but it can go back the other direction too. So if for some reason Bob wants to buy, coffee from Alice, the payment can go the other direction too. And that was also a difficult part of the technology, which I'm not going to go into right now. But it's basically a series of smart contracts that allow these different updates to occur in a way that there's a fallback. It's all about the fallback. That was the sort of the key insight that these guys provided, is how to do these fallbacks in a way that was secure. And then the last one is, at some point they just decide, okay, we're done negotiating, we're done, somebody wants to settle out their tab. Then they can, rather than wait for the timeout, rather than put that update transaction, which has these perhaps long, maybe a week timeout, then they can sign a new update, but this update has no timeouts. It's just immediately valid. And Alice can sign it and Bob can sign it, and then they can drop it on the blockchain. They maybe don't want to do that, but if they don't, ideally they keep this channel open and it goes back and forth. But once they've signed that, then it's locked, and they can put it on the blockchain, wait an hour, and then it's settled. Now, what happens if there's an uncooperative close? I guess I've talked about that already. So this is the situation where one disappears. Then they always have it in their back pocket, that last signed transaction. Does anybody see any problem with this? There is a problem that could occur. Anybody think about looking at this diagram, what might happen? Give you a hint that Bob has, or Alice has, all of these updates still in their back pocket, as it were. So what happens if Alice takes the one where she didn't pay anything and drops it on the blockchain? Because it's been signed now by both of them, and Alice could, in theory, try to get that on there before Bob can drop the transaction where he gets 3. So that's where the timeout is there. And in some, not only is there a timeout, but there's also a mechanism, at least in the Lightning Network. I'm not sure as much about Raiden, how they deal with that, but there's basically 3 that I'm aware of. Raiden does it some way that I'm not aware. There's another way you can do it where it's where Bob can basically make that previous transaction invalid. But the way that it's currently implemented, if you ever hear of something called a penalty transaction, it's set up so that if Alice drops an out-of-date transaction, she reveals a piece of information that Bob can now use to collect the entire channel, to collect all 10. So it's not just that it prevents a previous update from getting put onto the blockchain, but it also incentivizes Bob not to even give it a try. So that's one mechanism. There's debate about that, because the problem with that penalty mechanism is that, what if somebody's computer crashes and they restore from a backup and they have an old state where they actually had, one of these old transactions? Then you can get into a situation where somebody gets penalized. So this is still very new. I should have mentioned that before. I mean, probably the first implementations of this in the real world is only since, I don't know, I want to say March of 2000 of this year. So a lot of these issues are still being worked out. Another problem with this solution to the problem is that, what happens if Alice isn't there to see that what if Bob isn't there to see that Alice dropped an old transaction? So if Alice is offline, doesn't have an internet connection, or just goes away for a month of vacation, and doesn't close the channel, then you have this problem that you could get some old transaction put on the blockchain. There are solutions proposed for that, and some of them are kind of clever, but nothing's been implemented yet. But the one that I think is pretty interesting to think about is what they call a watchtower. So there's a way for Bob to basically outsource watching for a bad old transaction to go on the blockchain. So we can give a watchtower some kind of partial information. Doesn't have to reveal the actual transaction, but there's a privacy preserving way that can be put on the blockchain, can be given to some other party, so that if that other party sees an old transaction, they can drop it on the network and collect a little bonus for being the sort of watchtower over those set of transactions. So there's sort of an economy developing around these payment channels. So, but what I described to you was just Alice and Bob. What happens if Alice wants to pay Eve and doesn't have a payment channel with Eve? Now, sort of the dumb way to do it, the way that, like the simple way to do it would be just Alice has a payment channel with everybody. But that gets a little expensive. If you know there's 100 people you might spend money with, then you want to give $100, you want to prepay $100. That gets expensive quickly. And you can especially see for businesses, if every business has to have a payment channel with every customer, that might be an impediment for people using the system. Especially because then you also don't really scale that well, because now you still have to wait when you want to make a payment between two people. You still have to wait for that initial setup transaction, and you have to commit the capital, so you've got a liquidity problem. So these are reasons that payment channels alone aren't really a sufficient solution, but they're a key building block to make the rest of the system work. So now you can imagine that Alice and Bob, Bob and Carol, Carol and Dave, Dave and Eve. Multiple people have a chain of payment channels that take you between Alice and Eve, and what you can now do is you can discover this path. You can discover that that you can pay Eve through through Bob and Carol and Dave, and mostly what we're talking about here are micropayments. That's sort of the way this was originally conceived, because these intermediaries could take a fee. So they don't have to. They could do it for zero. But in the sort of ecosystem I was describing, you can imagine these some people will, or basically anybody could be one of these relays. You don't have to be a bank. You don't have to be have a blockchain company. Anybody can basically set this up. I have a little Raspberry Pi, if you know what those are. $30 Raspberry Pi at home that runs one of these Lightning nodes, and I just got 1 Satoshi the other day for somebody relaying through my node. 1 Satoshi is like a millionth of a Bitcoin, or maybe 100 millionth of a Bitcoin. It's quite a little bit amount. It's too little to actually spend, but I think the idea with these networks is that people will run networks and stay online so that they can facilitate this network of payments. So it works the same way as I described for two-party channels, but now you've got an extra little bit here, which is if Alice basically will promise Bob that they will give that she will sign this update for. Let me start again. So Alice wants to pay Eve. Alice, and in my example here, Alice wants to give 5 to Eve. So first thing Alice does is gives Eve some secret, and this secret is something that Eve has to basically keep to themselves, and then Alice negotiate, but Alice knows they have a payment channel through Bob to Eve. So Alice will go to Bob and say, their computers of course are doing this, if you can give me the secret that my destination has, then I will give you 8. And they write a contract. It's a smart contract. We were talking earlier about smart contracts. So it's a smart contract that says if you can provide the proof, and anybody knows cryptography, there's this thing called a hash function. It's a one-way mixing up of the data. So what the contract actually specifies is, they say, here is the mixed up hashed data. If you can give me the source, the pre-image that hashes to that, then this contract becomes valid. But if you don't, within some time limit, it doesn't. So that's between Alice and Bob. Bob does the same thing with Carol, but for a little bit less. So instead of offering 8, they offer 7. And that goes on. So this is how those intermediate nodes are incentivized to participate in the system. They don't have to take any payment, but that's the way it's conceived. And then eventually it gets to Dave and Eve, and Dave can say to Eve, if you've got the pre-image, if you've got the secret, then I will pay you 5. So you've bridged between. Now Dave is essentially doing what Alice wanted to do, and that's pay Eve. And Eve has the pre-image because Alice already gave the pre-image via some other source, via internet, via whatever. So Eve says, of course, yeah. So they sign a transaction. Eve reveals the information. So now when Eve, this little star thing, when Eve reveals the information, that contract immediately becomes valid So Dave could take that transaction and drop it on the blockchain and earn their one, since they earned on one side and they spent on the other, they would earn 1 unit. And Dave can go back to Carol can go back to Bob, and then Bob can eventually go back to Alice and prove that they have that pre-image. Now they also could, if Alice disappears or Bob disappears, if anybody disappears, they could just take it to the blockchain and basically say, look, I've got the pre-image, I've got the secret, I've got this contract, let's just settle this. It's just like the two-party system. But they don't want to, because that there's a cost and there's a time limit. So what they do instead, go back. Yeah, so what they do instead is they say, let's just sign an update that ignores that just says our last previous state is what we had this pre-image for. And then they sign that, because and the reason that Carol is incentivized to do that is because Carol and Bob and Alice, they don't want to close the channel, and they have the proof that it could be closed sort of without their participation. So they go ahead and sign something saying, okay, we're going to that's the new state. So now we're going to say it's 2837465515. So now you've just done a payment from Alice to Eve. There's been no blockchain connected. It can all happen on the internet within seconds. So it can happen at the same rate as your Visa. It can actually happen faster. Because it's all between pairs of nodes. So these are what they call, I just gave the abbreviation, a PCN. So you'll sometimes see that term PCN. It's a payment channel network. So payment channels between individual pairs of people, and then the network is building out this big network. And if they cooperatively update, then they co-sign an update that updates that assumes the last update was valid, or they do an uncooperative if somebody disappears. And people can go offline for different reasons. They may not be malicious. They may be just their computer connection went down, or their phone ran out of battery, or whatever. And I just mentioned one other thing is these PCNs, they aren't even, so not only could you do it on different blockchains, but you can do it between blockchains. So you have one of the examples of that is there's something called the Litecoin network. So Litecoin is it's a fork of Bitcoin. So it's essentially the same thing, but with a few rules changed. And one of the first examples to use the Lightning Network was this Litecoin. And they have demonstrated that they can actually do what they call atomic cross-chain Lightning transactions. And the way you can do that is you basically are running these things in parallel, but you use the same proof. So that proof that unlocks the transfer between two nodes can be mirrored on two blockchains. So if you basically transfer, if the transfer becomes valid on one, then the corresponding transfer going the other direction on the other can also be made valid. So that's a little maybe more complex to get into right now, but it's interesting to think about. It's not just payments, but you can also sort of do swapping of different things over these networks. And it's all because you're just basically swapping a secret, and revealing the secret is what makes it all happen. So now, given this network, how does that affect the dynamics of scaling something like, in this case, this is the Bitcoin network again. So Poon and Draya, they also did some estimates there, and they were looking at, so the previous case was 7 billion people making 2 blockchain transactions per day. You would end up with this 24 gigabyte blocks. That's a lot. That, we were saying that would be a very impractical scaling solution. But if you only open 2 channels per year, which is sort of an idealized, so everybody in the world's using them, and they're just opening and closing approximately 2 channels per year. Now you're looking at 133 megabyte blocks. So it's a couple of orders of magnitude smaller than you would have otherwise. And this, now if you talk about the scaling of technology, hard drives getting faster, networks getting faster, you're in the realm of what could actually be supported for every person in the world, essentially, to be using this network. So that's a pretty big improvement. And there are other technologies that'll probably bring that down. So I mentioned that there's this multi-sig address, so the multi-signature two-signer address. In the blockchain, the part that takes the most space is that signature. In Bitcoin, it's 64 bytes, and other blockchains that use different technologies, it's different also. But that's the part that you can't really compress in current technology. But there are other cryptographic systems you can use to make these signatures, and one is they call Schnorr signatures. That's a potential proposed replacement for the current signature scheme used in Bitcoin and Litecoin and a few of these other ones. What it allows you to do is, rather than one 64-bit signature for everybody who signs, it could be one 64-bit signature for many signatories. So if you had 2 people, it would be 64 bytes for both of them instead of 128 for both of them. There's also something called channel factories, if you want to look it up later. Channel factories essentially allow you to create these connections between pairs of people by first locking all your value into sort of a massive multisig. So you might have 100 people in one, and then they can reconfigure pairs of these channels. So pairwise, they can reconfigure pairwise in sort of multiple configurations, any configuration. So there's just one other way. So rather than settling your channel, or whether closing your channel to the blockchain, you can close it to one of these channel factories. So it still never hits the blockchain. So so even though doing 2 channel closes per year might be enough, you might even get it less than that, based on some of these other things coming down the pike. So that's kind of exciting. So that was my talk. It was a little bit quick.